Stan Gibilisco here, viewing an exploding star somewhere in an unnamed galaxy, in an unnamed galactic cluster, in an unnamed universe, in an unnamed set of universes, in an unnamed thought kingdom. Continuing the discussion of how to detect when a parallel resonance circuit is in fact tuned to resonance. The video that I made prior to this one on this very same subject with this very same diagram, figure 24-9 in the 5th edition of Teach Yourself Electricity and Electronics by yours truly and available on Amazon.com. This very same diagram shows two parallel resonance circuits in a preamplifier for a radio receiver. Here's the first parallel resonance circuit that goes to the input of this field effect transistor, the input electrode being the gate in an N-channel JFET in this case. Here is an output circuit, also a parallel resonance circuit. 200 picofarad capacitors, 2.5 microhenry inductances form a resonant frequency predetermined by the setting of this variable capacitor. The optimum is somewhere in the middle of the variable capacitor range. I forget exactly what the frequency of design is, but there's a formula for determining the resonant frequency of an inductance capacitance resonance circuit, either series or parallel. And that formula, the viewer mentioned, well, that formula is of no practical use. It's fine in theory. Well, it is of practical use in one sense. It'll give you an idea of the component values you're going to need in order to obtain resonance at a desired frequency. So whatever the resonant frequency I chose for this circuit is, it's probably either 7 or 10 megahertz. I chose 100 picofarads for the capacitance, which would be about in the middle of the range of this variable capacitor and this one, and then calculated the inductance that I would need and designed the circuit on that basis. Then, of course, this being a variable capacitor and this being a variable capacitor, in practice allows for precise adjustment of resonance. But the formula is useful for getting a ballpark idea of what these component values ought to be when you design the circuit. So I hope that I've answered that remark, actually it was, in the viewer's main question. The other thing is, where do you connect an oscilloscope, for example, to indicate resonance by peaking the amplitude of the wave that you see on the oscilloscope? Where would you connect it in these resonance circuits? Certainly not at the bottom of this one or the bottom of this one, because both of these points are at RF ground. This one through a bypass capacitor, and this one directly. And also, you wouldn't want to connect it to any point in this circuit without a capacitor in series with the probe that you use to detect the wave. Otherwise, the direct current bias, this 12 volt power supply voltage bias, would screw up the oscilloscope reading big time. It would displace the wave probably off the screen. So you put a blocking capacitor in series with the probe, probably 0.01 microfarads or something along that line. Then you can connect it either to this point at the top of this tank circuit or this point at the top of this tank circuit. Another name for a parallel resonant inductance capacitance circuit is a tank circuit, I guess because it's sort of like an energy holding tank. Once you've adjusted it to resonance, the impedance between this point here at the top of the coil and capacitor and this point here at the bottom skyrockets. When it's not tuned to resonance, the impedance is relatively low, and that's how we get a peak in the amplitude of the signal here and the amplitude of the signal here, and consequently also here. The signal peaks at resonance because the high impedance of this tank circuit opens up that short circuit to ground. When it's not tuned to resonance, in effect the impedance is very low, and this is shorted for radio frequency signals to ground, and you get only a minimal amount of gain or even a loss. So that's why you see a resonant peak here, even though it appears, if you connect the probe here or here, that the signal coming in and the signal coming out are both at the same circuit point. How does that work? I mean, how can that be, you might ask? Well, that's how. The signal itself is shorted out to ground most of the time, except when this circuit or this one, or preferably both of them for optimal circuit operation, are tuned to resonance, so that these impedances become very high, and it's like opening up a switch and letting the signal on through instead of shorting it to ground. So you would connect the probe here, even though it appears you're connecting it to both the input and the output point for the signal, or here, and where it also appears that you're connecting it either to both the antenna input and the transistor input at the same time. So hopefully I've answered that question without muddling things up too much. But the question of where to put that probe, again with a series blocking capacitor to prevent DC getting in the way of the performance of the oscilloscope, the point to connect that probe for the input would be here, assuming your oscilloscope is sensitive enough to detect that signal, or here. I'd connect it here and then adjust both of these tank circuits together until you obtained the greatest possible signal amplitude here. Then you would know that both of these tank circuits were tuned to resonance. You'd know that in practice they actually were. It wouldn't matter then what the value of these capacitors actually was. The formulas are not relevant for that purpose. They're only relevant for obtaining the values that you should start out with in order to design the circuit so that when you finally do put it together, it's most likely to work. That's my limited amateur radio experience. Amateur radio call sign W1GV, Whiskey 1 Good Vibrations, and author of Teach Yourself Electricity and Electronics, 5th edition. You'll find that diagram in this book along with a lot more related and unrelated information about electronics, a complete electronics course. I will provide a link to this book so you can buy it. Please don't pirate it. You can buy it at Amazon.com. Or, of course, you can go to your local bricks and mortar bookstore and hope that it's there. Hope that there's even a bricks and mortar bookstore anywhere near you anymore. Meanwhile, things are a lot simpler, even in the vicinity of exploding stars in unnamed universes containing unknown sets of galaxies, containing unnamed clusters of galaxies and galaxies themselves, containing unnamed solar systems. I'll bet the planet orbiting this star is having a pretty rough time of it right at the moment. Hope you've endured me for this long. It's all in fun, really, in the end. If you don't have fun, you don't have a life, say I. Stan Gibilisco signing off. Until next time, so long.